Hello everyone, welcome back to another physics paper. This time we are attempting alternative to practical, paper 6-1, October-November 2025. So, let's get started. Question number 1. A student investigates the balancing of a meter ruler. Figure 1.1 shows the apparatus, okay? Here we have figure 1.1. For part A, the student places a meter rule on a pivot of the 50 centimeter mark. She places an object Q with its center on the meter ruler at the 90 centimeter mark. Okay, so they want us to determine the distance y, which is this one over here, from the 50 centimeter mark, which is the pivot here, to the center of the object Q. Okay, so what we know here is that it is a meter ruler, which means that it is a total of 100 centimeters. And the center here, which is the pivot, will be at the 50 centimeter mark, so exactly at the half. So the total distance here is 50 centimeters. We know that here this is the 90 centimeter mark. So since this part here, because as it's at the end, that part here will be 10 centimeters, this would mean that this whole part y will be 40. And we can actually prove that by adding 40 and 10. So you have 40 plus 10, you have 50 centimeters. So our answer here will be 40 centimeters. And as you can see, it is correct to three significant figures, so our answer should be as well. Okay, so for part B, she places a 2 Newton load on the meter ruler. She adjusts the position of the load so that the meter ruler is as near as possible to being balanced. She measures the distance x from the center of the load of the 50 centimeter mark, which was 21.5 centimeters. Alright, so if we want to go back, this is the load in question. This is the 2 Newton load. 2 Newton. So this was placed at the 21.5 centimeter mark. So this distance here is 21.5. Although it doesn't seem like it in this apparatus over here. However, after all, this figure here is not up to scale. Okay, so let's see what they want us to do here for part 1. Calculate the weight W of object Q using the equation W equals 2x over y times 2 Newton. So we don't really need to derive anything. The equation is already given to us, so we just apply it. Give your answer to a suitable number of significant figures for this experiment. Since all of our figures here were three significant figures, we should do as well. So our answer here should be about 21.5 over 40 times 2, which arises to, let's calculate that, the 21.5, divide that by 40, multiply that by 2, you get 1.075. Then that will be 1.08. 1.08 newtons. Okay, so I want you to notice how we are rounding to three significant figures, although our data here, like so and so, would seem to be that we are rounding to one decimal place. However, in physics, we don't really round to decimal places. Rather, we round to significant figures. So if here we had 1, 2, and 3 significant figures, so should our answer. It should also have 1, 2, and 3 significant figures. Okay, now let's move on. She repeats the procedure using a 3 Newton load. She does not change the position of object Q. Calculate a new value of the weight W of option or of object Q using the equation W equals to x over y times 3. Okay, so basically, she did the same thing that we did here earlier for the weight. However, instead of the weight being of 2 newtons, now it is of 3 newtons. So we are just ever so slightly varying the equation to suit the 3 newton weight compared to the new or the 2 Newton one. So if we do the math, that will be 14.8, our new value for x, over y, which was 40 times 3. So once again, we use our friendly calculator. So 14.8 divided by 40.0 multiplied by 3, which will be 1.11 Newton. And we don't really need to round anything since it already is two three significant figures. Okay, so 1.11, that should be our answer. No need to round anything. So moving on to part C. State and explain whether your two values of W are equal within the experimental limits of accuracy. So refer to the values of W in your answer. Okay. For this one, we need to do some calculations, particularly the percentage change calculation. So if you want to assume that this value here, 1.08, is our initial value, and this value over here is our final value, and we use the percentage difference formula, which should be final minus initial over initial times by 100, then that should be 1.11 minus 1.08 over 1.08 times 100. So if you try to do that, then 1.11 minus 1.08, you get 0.03. Divide that by 1.08, then multiply that by 100. What do you get? You get 2.77. Or two significant figures, that will be 2.8. Now, what is allowed in the range of experimental accuracy is 10%. So since 2.78 is less than 10%, then they are said to be equal. So the statement should be yes, they are equal. So explanation will be percentage change equals 2.78%, which is less than the allowed 10% of experimental accuracy. Okay, that should do. So that's that. Moving on to part D. Explain how you ensure that the center of object Q is directly over the 90 centimeter mark of the meter rule. You may draw a diagram. Okay, so let's get back and see what they mean here. So they're mentioning or they're referencing to option Q or object Q, I mean, which is this one over here. So object Q, this one, they're saying that they want to ensure that the center of object Q is exactly at the 90 centimeter mark. And they want to ask us about how. Now they are suggesting that we draw a diagram, but that's optional. That's why they said may, but if they said you have to draw a diagram, then you have to. So basically here, I'd say that the best way to do it is to use a vernier caliper. So use a vernier caliper here, for example, just as an example. So this vernier caliper, you see the thickness of object Q. Let's say if that thickness was 10 centimeter, then you know that the middle here, the midpoint, will be at the 5 centimeter mark. Okay, so that will be at the 5 centimeter mark. So now you know that to ensure that object Q is at the center at the 9 centimeter mark, then that would mean that you have to place the starting point of the object at the 85 centimeter mark to make sure that the center here is exactly at the 90 centimeter mark. Because since this distance here from the start towards the middle is 5 centimeters, so if you put it at 85 centimeters and then we add the 5 centimeters, which is the same distance from the start of the object towards the center, then that will be exactly 90 centimeters. So that's the technique that we should do. So personally, I will not draw a diagram here, as I kind of did here while explaining. So this is the way that I will write it. Use a vernier caliper to obtain thickness of object Q, divide by 2 to find the distance from the end of the object towards the midpoint, then place the end of the object at 90, like on the ruler itself, at 90 centimeter, minus the distance between the end of the object and the midpoint. So that's basically it. Now I worded it that way so that it can be like more obvious for you, because I just explained how we did that in this diagram here. However, if you will, or if you want to explain it to the examiner, then if you want to, you can add, for example, an x. You can, like, for example, label this distance x and then do 90 minus x, for example, if you want to do it that way. Now for E, it is difficult to find the position of the load to obtain the exact balance of the meter rotor. Explain how you try to overcome this difficulty. Okay, basically, they're saying that when we want to add the load to the meter rotor, then it isn't really obvious or it's not really easy to find the exact spot in which it will make this rotor balanced. So how do we find that position? So basically, you have two ways. You can either move the load back and forth multiple times until you find like the range in which the load can be balanced, because it isn't always the exact millimeter that makes the roller balance. It could be that, for example, if you place the load here, or here, then they all will cause the rotor to be balanced. So, since we don't really have an exact millimeter or an exact midpoint, then we can just move the load back and forth for us to get the range. And the range being, of course, this distance here, the overall range. Or you can move it at different points again, like maybe here, here, or here, and then you find the average. Okay, so that's basically what I would do. Or you can combine them both, like both ideas, which is exactly what I'll be doing right now. So move the object back and forth to find the range in which the rotor is balanced. And take average. So basically, for example, if here, this point over here was like, let's say 22, this point here 22, and this point over here was 21, for example, then the midpoint here would be about like 21 plus 22 over 2, which would be about like 21.5. So that's the idea, essentially. Okay, so here we have part F. Figure 1.2 shows the meter rotor balanced on the pivot with no loads. The balance point shows the position of the center of mass of the meter rotor. So basically here, we don't have any loads, so no loads. It's only the rotor by itself. So whatever this point here is just essentially the exact center of mass of the rotor by itself. Determine the distance between the 50 centimeter mark on the meter rotor and the center of the mass. So the 50 centimeter mark was here, as you have seen it in the figure 1.1 in the image. So here, they're saying that the actual center is at this point here. So they want the exact the exact distance d between the 50 centimeter mark, which is this one over here, with the center of mass. So they only want this distance here. This is d. So let's read. So this is 49.5, 49.6, and 49.7. So to get the distance d, that will be 50 minus here, which was 49.7 as we discussed, which would ultimately be 0.30 centimeters. Okay, that should be enough. So 0.30 centimeters. Alright, so for question number 2, let's see what we have here. A student investigates the resistance of a wire. Figure 2.1 shows the circuit he uses. Here A. Record the ammeter reading shown in figure 2.2. Okay. Alright, so you can see here that we have intervals of 0.2, which would mean that the midpoint here, this point here, which is at the fifth line, that should be 0.3 because it's exactly between 0.2 and 0.4. So that means that here, between each 0.1 amperes, we have 5 lines that separate it. So if you want to divide 0.1 over 5, then essentially that will be 0.02, 0.02 amperes. So here that would mean that this line over here, that will be 0.3 plus 0.02, which means 0.32 amperes. Okay, so 0.32. Okay, moving on. The student places the sliding contact 15 centimeters from B. Okay, this is the sliding contact. So that should be 15 centimeters. Okay. He measures the potential difference V across the length D equals to 15 centimeters, as we discussed, of resistance wire BC. He repeats the procedure using values of D equals to 40, D equals to 60, and D equals to 80. So he first tried with 15, and then he moved on to 40, 60, and 80 respectively. The values of dV and R are shown in table 2.1. The voltmeter reading he obtains when D equals to 100 is shown in figure 2.3. Okay, so this is what it looks like when it was 100 centimeters of resistance wire. So since this is perfectly between 2 and 3, this should be 2.5. 2.5 volts. Okay, so since here we know that this is 2.5, then we can calculate the resistance using the formula given. However, before anything, you have to complete the column headings. So the distance here, as we discussed, was in centimeters, so that will be cm. V, which is the voltage, will be in volts, and the R resistance will be in ohms. So let's find out what the resistance at 100 centimeters would be. So R equals to V, V being 2.5, and if we take a look back, we would see it's a series here. It's a series circuit, which would mean that this current reading here will always be constant. So it's always 0.32. So it is 2.5 over 0.32. If we use our trusty calculator here, so 2.5 over 0.32, that would be 7.8125. However, since all of our values here are to three significant figures, that would be 7.81. Okay, so that's that. Let's see what we have here. For part C, plot a graph of resistance R in the y-axis against length T in the x-axis, drawn a best fit line. Okay, so we should draw a best fit line here, or more specifically, we have to. So, first of all, we need to plot, and we need to make the indications or the labels. So, on the y-axis here, that will be R in ohms, while here that will be D in centimeters. Okay, so we said that here we have 15, 40, 60, 80, and 100. We don't really need to start from 0, but let's see if we can. So if we did 0 here, let's see first how many divisions we have. We have 1, 2, 3, 4, 5, 6, 7. Okay, so if we did by 10, that will not work because you have, even if you start at 10, by the way. So you have 10, 20, 30, 40, 50, 60, and 70. You can see that's not enough. What you can do instead is that you can start at 0 and then go up by 20. So 0, 20, 40, 60, 80, and 100. We have one extra, which is okay, that's good. And then we can do the same for the resistance. Now resistance is a bit variable, you can see here. You have 1.25, 3.44, 4.38, 6.57, and 7.81. So minimum value, if you just want to take the absolute minimum, that would be 1.00. Maximum will be 8.00 on the plot, of course. So let's see how many divisions here we have. We have 1, 2, 3, 4, 5, 6. 6 divisions. So once again, we can just do 0, 1, 2, 3, 4, 5 because that's not enough. And we can just do 1, 2, 3, 4, 5, 6 because here we have 7.81, which reaches to 8. So maybe we need to do the same thing and start at 0, and then we do 2, 4, 6, 8. I think that's reasonable. So 2.0, 4.0, 6.0, and 8.0. Now, of course, you can do, for example, 1.5, 3, 3.5, and whatever. However, even if that fits the line, then I wouldn't say actually that it's the most friendly to do a calculation. It's not the most calculator friendly. Because some points can be right in the middle and in like ugly points, which will actually make you solve a bit slower because it's more confusing. So I think this is the ideal way to do it. So let's go ahead and plot. So at 15 centimeter, we have 1.25, okay? All right, so 15 centimeters. So if this is 10, then 15 is the middle between 10 and 20. So that is 15. That's 15 here. Okay, and it is 1.25. Okay, so let's see what each line here equals to. Since here we have 10 divisions and intervals of 2, then that means that each line equals to 0.2. Okay, so here for 15, this here should be 1, and this should be 1.2. Here should be 1.24. I mean 1.4. Okay, since we want 1.25, then it's somewhere in the middle here. But it's not in the middle because that'll be 1.3. So it'll be a quarter, which is somewhere like so. It's okay if you don't put it accurately because in the marking scheme, after all, it is basically accuracy up to half a box. So whatever you do between that point here, then you're good to go essentially. Okay. And also remember that whatever scale you want to choose, it has to be more than half of the graph, always. Okay, so that's one done. The other 43.44, you can round that to 3.4 if you want to. So 40 is here, 3.44. Okay, so that's 3. This is 3.2, 3.4. So 3.44 will be around here. Now it's okay if you do it 3.4, but I like to be a bit more accurate, so I just do it like so. And always remember to use crosses rather than dots, because dots aren't so accurate. If you want to use a dot, then you can do something like this. That's the only acceptable way. But it's always recommended to use crosses rather than dots. Okay, so moving on, here you have 64.38. Okay, so that's like about 4.4. So here you have 60. That's 4, 4.2, and 4.4. Okay, we're done with that. 80 is 6.56 or 6.6. Type 80, 6, 6.2, 6.4, 6.6. That should be that. Okay. Then what we have here is that we have 7.81. Okay, that is interesting. So that would be 7.8. 100, that's 100, that's 7, 7.2, 7.4, 7.6, and 7.8. Okay, it seems that oh, that's a bit not too accurate. That should do the job now. That should do it. Okay, so now if we want to make a line of best fit, it would fit like a glove, except for this point here, which can be an anomaly. However, there isn't any mention of an anomaly, I believe. Okay, so the next point here is drawing the line of best fit. So let's see, you have to make sure that all the lines should have about, or like the line should have about the same number of crosses on each side, and it should always be like close to the line or so. So here I think that'll be good. We have 1 point going across the line, so it's neither in the middle. And the rest we have 2 on top and 2 in the middle, or like 2 under. So I think that should do the job, the trick. And it also fits actually. It's right from the origin, which is also good. So it's not always going to be on the origin, but for this case it is. So that's a nice drawing here. Okay, so use your graph to determine the resistance R75 of a length D. D equals to 75.0 centimeters of the resistance wire. Show clearly on the graph how you obtain the value. So you have to draw on the graph. So you have to find D equals to 75. So we can do the same technique of 15, in which the middle between 60 and 80 is 70, which would mean that the middle of 80 and 70 is 75. So this is 75. This is like a quick way to do it. So now the way to do it essentially is to draw a line like so into here. So you can see it's actually on the half here, right on the half. And then we draw a line all the way here. So it's half a box over 6. We said that each box here would be 0.2 because here we have intervals of 2 and we have 10 divisions. That would mean that each half box will be 0.1. So this will be 6.1. 6.1 ohms. 6.1 ohms. And that's that. Okay, we are done with question number 2. Okay, so far so good. Let's go on to question number 3. Okay. A student investigates the refraction of light in the material of a transparent block. Figure 3.1 shows the ray trace sheet. The student places a transparent block on the sheet and labels the block A, B, C, D. Okay. On figure 3.1, draw a normal NL to the side of AB to the transparent block at a distance 2 centimeters from A. Okay. Continue the normal so that it passes through the side CD of the block. So we draw a line. For example, let's say that this was 2 centimeters, let's say. Then overall, this part here, this should pass through CD. So we draw the line at AB, and then we extend it to CD. Essentially, that's the idea. Okay. Anything else? Yep. Label the point S where NL crosses AB. So when we draw the line, here that will be S. Okay, so let's see what we can do here. Okay, so we got a ruler here. Let's place that here. Okay, now this is not really two sides actually, fortunately. So this apparently, according to this drawing over here, or this ruler, this point here is the 2 centimeter mark. Now, of course, it'll be very different for you. I don't believe that this will be 2 centimeters. However, what I'd say is that you use your own line. Okay, so let's first of all just plot what 2 here. This is 2 centimeters. This point here. So I'll just remove this one over here for now. This is the 2 centimeter mark. Essentially, what you should do is that you should draw a line right through. So you should use your own ruler and see if this is 2 centimeters. Now, I do not believe so. I think 2 centimeters should be around here. So to be more accurate, I think that I will shift this point here a bit, because after all, this is just a photocopy, and it won't exactly be 2 centimeters per se. So instead, let's say that this is 2 centimeters. Let's say this is 2 centimeters, and then they want us to label it NL. So N here and L here, or vice versa. And this point here will be S, as we said, because it is the intersection point. Okay, and since the line does cross C and D, we are good to go. So let's see what part B says. Draw a line RS to an angle I equals to 30 degrees to the normal above AB. So above, it has to be like so. It shouldn't be like this. Okay. The student places two pins, P1 and P2 on line RS, mark with two crosses X on line RS, positions of the pins at a suitable distance apart for this experiment. Okay. Again, I don't really have a protractor here, of course, because I'm using a laptop. So you should use a protractor, but here I will estimate. So if this is 45 degrees, then this should be 30. So this will be 30 degrees, that's 30 degrees, but you should use your own protractor. And then they said that we should point or plot 2 points here as x's, and which that will be P1 and P2. I think it's wise if we also label it here. So that's P1 and that's P2. Okay, sounds good. Now, let's see what we have here. The student looks from the position of the eye shown in figure 3.1 to observe the images of P1 and P2 through the side CD of the block. He adjusts his line of sight until the images of P1 and P2 appear exactly one behind the other. Okay. He places two pins, P3 and P4, between side CD of the block and his eye so that P3 and P4 and the images P1 and P2 seen through the block appear exactly one behind each other. The positions of P3 and P4 are shown on figure 3.1. Draw a line through the positions of P3 and P4. Continue the line until it meets the normal and L, and label that point E. Okay. So essentially here, we should draw a line from P4 to P3. A straight line, of course. Now this is not so straight, so I'll just correct that here. And that should do the trick. Okay, so this is exactly how it should look like, right? It's looking very good now. So let's see what they're asking us to do. Oh yeah, I forgot to label it actually. So this point here, let's see what they want to say. So label that point E, which is the one that it means the normal NL. So that is E. So that's E, and they want the other end to be F. So this should be F then, apparently. Okay, so E and F, alright. So they want us now to find this angle here. So we said this angle here was 30 degrees. This angle here is quite similar to that, from what it seems. So I'd say that this is 33 degrees or 32 degrees. So I'll put that as 33 degrees. Now, of course, you have to use a protractor here. Again, I don't have a protractor because it's digital. So I can't really use a protractor here. However, if you actually use a protractor here, this has to be exactly 30, and if you did everything right, then this one here should be 32, 31, or 33. That's according to the marking scheme. Okay, so that is 33 degrees. Now on to part D. Take one box to complete the sentence. To produce the most accurate rate trace, a student places pins P1 and P2, which are these two here, exactly 5 centimeters apart, less than 5 centimeters apart, or more than 5 centimeters apart. It should be more. As much distance as you can put between these two, the better, because it'll be more accurate. That's a rule of thumb, okay? It's a rule of thumb that you should always follow. So this one, no question, should be the last one, okay? Alright, now suggest two other techniques that the student can use to produce an accurate ray trace. Okay, so since here we are using a pencil, one of the best ways to do it is to use a thin pencil. So, like draw the lines here, like the normal whatever. This has to be using a thin pencil. So, use a thin pencil to draw lines. Use a thin pencil. Alright, now what else can we do? Okay, maybe we can do something about the pens themselves. Now the pens, you can make it better by two ways. Either you make sure that they're exactly vertical, like when you do a pen here, this pen, let's say that's a pen, you have to make sure that the other pen is completely vertical as well. It won't be like slanted or kind of like so. Because then it will be very difficult or like it won't even be possible that this will exactly be behind this. It will be inaccurate. And sometimes it can look that they're exactly behind each other, but in reality they're not. And the same thing if the pens themselves were wide. If they were wide, then for example, let's say that this one over here is not exactly centered. Let's say that it's slightly to the left. Okay? It will not show because your eyes will be from here. Okay? This will be your view. Okay? This will be your view. So, essentially, because even though, although this one here is like to the left or to the right, it will not show because this part here, because it is big, it will cover it completely. Either ways, even if it's centered or not. So if we use a thin one, then we can spot this difference and adjust the pens accordingly. That's the idea. So I will use, you can use either point, but I will use a thin pen. Use a thin pen. Okay. The student plans to investigate the relationship between angle I and angle theta. The student takes more sets of readings to test the relationship. List suitable values of angle I that the student can use. Okay, first of all, what was angle I? Okay, so angle theta is this one here, which was this. This is theta. And I believe, is the incidence one. This is I. So this is I, which was 30 degrees, 30, which is here. Yeah, indeed. It is 30 degrees. And this one over here is theta. And we want to see the relationship between them both. So we want to have a variety of angles. That's the theory. Okay, so we can do angles that are both less and above. So for example, we can try 20, then 40, 50, 60, and whatever. And then we can see theta and compare if they're similar or not. So here you should use at least 3. I will use 4. So I'll use 20, 40 because we already used 30, 50, and 60. Okay, that sounds good. And we're actually done with question number 3. Okay, that's nice. On with the last question, question number 4. A student is investigating the electrical heaters that are used in the school laboratory to heat beakers of water. Okay, so we have electrical beakers or electrical heaters that will heat the beakers of water. So it acts kind of like a water bath. The heaters are all 12 volts heaters with the same power rating. Okay. The student thinks that some heaters are more efficient than other heaters. Plan an experiment to compare how quickly the heaters increase the temperature of water to boiling point. Okay, so here, how quickly the heaters increase the temperature of water. So we can assess that by time. So here, the dependent variable, which is the variable that we test for, or the variable that we actually observe, that will be the time. So dependent variable will be the time. Dependent variable, that would be the time. Meanwhile, the independent variable here will be the beakers or like the heaters themselves. Because it says that the students thinks that some heaters are more efficient than others. So we actually vary the heaters. Okay. Now the following apparatus is available to the student. 5 electrical heaters, beakers, supply of water, 12-volt power supply with suitable leads. Okay, other apparatus normally available in a school laboratory can also be used. In your plan, list any additional apparatus required. Explain briefly how you do the investigation, including the measurements you take. State the key variables to be kept constant, and draw a suitable table with column headings to show our readings, but we don't really put any readings. And explain how you use the results to reach a conclusion. Okay, so if you want to actually put that here, then I recommend that you use a template for that. First of all, we have the independent variable. Then we have the dependent variable. Then they ask for the control, the stuff that we need to keep constant. Yes. So we should also put the control variable. I will leave about 2 lines for this. Then the method, which is basically how we carry out the experiment. Do they want safety? They do not. But still, I will include safety. But before safety, we'll include conclusion. Conclusion, like how we can conclude our method. And at the very end, we can include safety. Safety precautions. Okay, so first of all, now although we're not required to actually draw an actual apparatus, but I will still do so because it helps you to visualize it. So essentially here, let's first start off with the beakers themselves. So we have the beakers, and these beakers have to have a standard volume. Then you have water. Now to reach the boiling point, you have to know when it's exactly reached, and that is by, of course, using a thermometer. So that's something that we need to do. We need to add a thermometer. And to keep the thermometer in place, we would need a clamp and you would need a lid as an insulation. So we put the lid. Here, that's a lid. That's a thermometer. That's a clamp. And we would also need a heater. So we can actually put also a gap in the lid for the heater. So the heater, it would be a coil, for example. Like that's usually how heaters would look like. So we add a coil that will act as a heater. For example, now it's not literally a coil, but just for demonstration purposes, that's a coil, or a heater, I mean, connected to power supply. So we also need to standardize the power supply. Okay, that's good. And to make sure that everything is kept constant, now the lid is actually here, we should also add insulation. So this part here will be insulation. Okay, so and also we need a stop clock, of course, a stopwatch to measure the time. So this is a stopwatch here. Let's draw a nice one here. Okay, so we have this stopwatch, we have the power supply, the heater, the thermometer to actually see when it reaches 100 degrees. Then we have the clamp. I think that's very, very good. Okay, so we don't really need anything more than this. We don't need anything fancy. For the table, so I'll just draw maybe this for now, but I think that it's always better to draw the table at the end because now you have actually a more clear structure of how you're going to do things. So, since we have an overall draft, we can actually put all the stuff together. So, For the independent variable here, which is the variable that we change, that will be the beakers. So five different beakers, I mean heaters, I mean. Five different heaters. The dependent variable, okay, which is the one that we actually measure, then we're going to measure the time taken to reach boiling point. So time taken to reach boiling point. Okay, the control variable, the things that we keep constant. So we want our beakers to be constant, of constant size. So that's one, because of course, like if it's wider, then the evaporation will be faster. So size of beakers. We also want to standardize the volume of water, because the volume does play a role here. So volume of water. Okay, what else? Ah, yeah, since we have a power supply, then we need to standardize the power supply. So power supply. To make it more visible, I will just add an underline under here. All right. What else do we keep constant here? Okay, the wind conditions maybe, the wind speed, because if the wind speed is higher, then maybe actually it can like influence evaporation, yeah, it be faster, which can mean that the boiling may also be faster. Hmm. Okay, now not sure if that would be right. However, just to be safe, I'll just add conditions. Okay, so environmental conditions. Also, one very important factor is the initial temperature of water. So, initial temperature of water. Because if it was hotter, like already as like 80 degrees, then it won't take long for it to be 100 degrees. So, initial temperature. Though if it was like actually that's an interesting fact. If it was very cold already, then it will take faster to boil. So that's something. So we should make sure that the initial temperature is somehow constant. Now we actually start with the method. Okay, so I like to number it like 1, 2, 3, 4, etc. So our first step is first of all to set up the beakers and add a specified volume of water. So add volume or like a constant volume of water to beaker. Constant volumes of water to beakers. Okay. Then we suspend the thermometer using a clamp. Like you try to engineer the method such as it's like easier for someone to read it and actually follow it. So suspend thermometer using a clamp. Maybe it's actually wise if we add a switch. So if we add the switch somewhere here, for example, like to turn it on and off. Yeah. Okay. So you can also what you do is that you can say that we will connect the heater to the power supply. Connect heater to power supply. And keep switch open. This is so that like it doesn't like immediately start heating. So keep switch open. What we can also do is that we can add, for example, a glass rod. Like we can actually add some space here for a glass rod. So you can see that like the ideas start coming one by one. So you start actually kind of like drafting and then you start having the ideas. So this is the glass rod. Why? Because we want to essentially stir. We stir using the glass rod so that the temperature is constant throughout. And of course, this will be our lid. I'll just put that label here. Okay, so add lid and insulation. And then we can also, as we said, use glass rod to stir and to make sure that the temperature is constant. Use glass rod to stir and ensure temperature is constant throughout. Okay, and then from here actually we turn on the heater by closing the switch and we start the timer. So close the switch to start heater and immediately start the stopwatch. Okay, so that's what we do. Immediately start the stopwatch. Okay, now as we are done with this point here, since we started the stopwatch, then we also need to define when we stop it. So stop stopwatch when the thermometer reaches 100 degrees, or boiling point to be more specific. Stop stopwatch when thermometer reaches the boiling point. And then we record the final temperature. Actually, we missed a step, yeah, like actually. So yeah, I think some of you already have seen that. Before we start and close the switch, then what we should be doing is that we should take the initial temperature first. So this is 7 and 8. So take initial temperature of the water, because after all, we want to keep the initial temperature constant. So take initial temperature using thermometer. Okay, so after we are done with that, what we should be doing is that, like, after we record the final temperature, then what we do is that we redo the experiment using the same heater, okay, using the same heater, and then we take the mean to ensure that we have like a variety of data and to make sure that our data are accurate if we take the mean. So let's say let's take at least 3 readings, yeah, at least 3 readings using the same heater and take mean. And then we repeat the experiment using the other heaters. Okay, now how do we conclude? So here we actually conclude from the table, or we can actually also draw a graph. Okay, so that's the point I will use the table. So let's say that use the table. Use table to compare the data or like the time. Use volume to compare the time. And observe if the thermometers or like the temperature or the time actually to be more specific, since after all we are doing this experiment about the time. So if the time varies depending on the thermometer or like the heat. varies depending on the heater. Okay. Now, safety shouldn't be something that's like out of the ordinary. You can just say that you use like electrical resistant gloves, for example, or you stay away from the boiling water. So, I'll just write both. Use electric resistant gloves, stay away from boiling water. Okay, and that should be it. Though we should, of course, draw our table. So for our table here, okay, so we want, after all, to test depending on the various heaters. So we'll do here heaters. How many heaters we have? We have 5 heaters. So we should have like 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Now we should also, of course, add an extra row. 1, 2, 3, 4, 5. It would be wise if I made this one a bit bigger. And this is exactly what I'll be doing now. Now, of course, you can do this in the exam, obviously. So you should plan your drawing well. Okay. So the first one, or the first row that I will actually take here is the initial temperature. So initial temperature, and do not forget the degrees Celsius. And then you can take, like, as we said, the 3 different values for temperature and then the mean. So this is what I will write here. So T1 degrees Celsius, T2 degrees Celsius, T3 degrees Celsius, and then T mean degrees Celsius. And that should be it. Okay, I think that's the perfect model answer. Alright, so that's that. We are done with this question. We're done with this whole paper after all. So, I'd say that if you have any questions or like anything that you didn't see as straightforward, then you should come back and then do some of the questions again. And that's that for today. See you all in the next paper. Goodbye.